Okay, looking good. So what I'm going to talk to you about today are two research projects. Both of these are ongoing, but they each are separate in how they address how trees interact with stormwater in terms of the stormwater quantity and quality. They're both located here in Wisconsin. The Stormwater Quality Project is located in the capital of Wisconsin, in Madison, and the Stormwater Quantity, which really kind of focuses on tree canopy, is located a little bit further to the north in the city of Fond du Lac, Wisconsin. So I'm sure most of you on the call are probably pretty aware of why we are concerned about nutrients in urban stormwater and the effect they have on our receiving waters. These photos to the left are taken from here in Madison just last year, or 2018, 2019, and it's kind of becoming a repetitive situation every summer where we have basically over-fertilization occurring from our urban environments that pass along phosphorus-rich runoff from urban land use into a very efficient conveyance system, and by way of storm sewers, which ultimately dump into either a lake or a river system. And as the weather warms up, we get this nasty green mess of cyanobacteria blooms and harmful algal blooms, which of course causes a reduction in recreational loss. Nobody really wants to swim or boat in that kind of muck. And then there's these health concerns that are associated with it. So what do you do about it? Well, for many years now, both EPA and state Departments of Natural Resources, Environmental Protections have been working on total maximum daily loads, or a TMDL, for various types of pollutants. Total phosphorus is one of those. The city of Madison is, like many other cities around the country, have a TMDL for total phosphorus. So they're charged with reducing the amount, the pounds of phosphorus that they contribute to the receiving waters every year. And they're trying to figure out how to do that. So some of the obvious ways, of course, are to use structural practices like rain gardens or bioswales or other forms of green infrastructure or wet ponds. But it's becoming increasingly clear now that in many ways, you're not going to be able to achieve that TMDL through structural practices alone. So you need to start looking at other methods. And one of those, at least within the urban environment, is to do source control. Leaf collection in the fall was an obvious part of that equation, but there's really a lot of uncertainty as to whether leaf collection, municipal leaf collection anyway, would result in any meaningful reduction in phosphorus loads in stormwater. So that was the genesis of this research project, to determine whether leaf collection could result in total phosphorus load reduction, and if it did, what can you do by maybe changing the way you collect the leaves to maximize that reduction? So this made sense for us to incorporate a classical paired basin study design where we have a control and a test catchment. Both of these are located in Madison, Wisconsin, and then we've kind of branched out into other cities around the state. But the basic idea here is that you have two catchments that they really don't even have to be similar to one another, but that you measure the relationship between the two when they are during a calibration phase, when they're equally treated. And in this case, we're measuring how total phosphorus and dissolved phosphorus and other nutrients respond to each other after a runoff event. And then you follow that up the following year with some sort of treatment. And in this case, the treatment was leaf collection done in the test catchment, whereas the control catchment was left without any leaf collection at all. And then you measure the change in that response between those two, and then that change would then, of course, be due to leaf collection, and you can quantify it. So that sort of sets the stage of the basic statistical design behind our research project. So this chart shows you the results of that effort during the calibration phase. So each of those lines on the chart represent the average total phosphorus concentration per month in both the control and the test catchment. And then above, you can see I placed some photographs kind of showing you what the condition of the street and the trees look like during each month of the year. And it kind of makes sense. And there's two things really to take away from this chart. One, is that both of these catchments under a no leaf collection scenario act fairly similar to one another. In other words, we have a relatively low concentration in April, and if you look at the photo, you can see why. The leaves haven't emerged yet. The streets are still relatively clean. And then in May, we get a little bit of a bump there in concentration. Now you can see that leaves are starting to emerge. That means there's pollen, there's seeds, there's buds that tend to concentrate within the gutter of the street. And consequently, we see an increase in phosphorus concentrations. And then, all the way from June through September, it's relatively a constant baseline concentration. And these probably from other sources of phosphorus other than leaves. But then you see this maximum concentration in October, and where you have leaf senescence that tends to accumulate within that gutter line, and now the amount of organic detritus that tends to accumulate is very significant. And as such, you see the response in concentration. It really far overwhelms any other monthly concentration that we've seen in the past. And then by November, a lot of those leaves are already gone. Any remaining on the street, a lot of the phosphorus may have already leached out. There are no new sources of leaves coming, and so we see a little bit of a dip. So this is sort of our baseline calibration condition for both the control and the test catchments. What we wanted to do after that was impose some form of treatment. And before we went on and started testing various types of municipal leaf collection practices, it was important for us to be able to say, well, can we get any measurable reduction at all? Is it statistically significant if we do our maximum effort? And our maximum effort was interpreted as making sure the streets were as clean as possible right before a rain event. Because if we couldn't see any difference with that sort of condition, then there was no way we were going to see any difference by some sort of municipal leaf collection effort, which would be something less than this maximum effort. So that looked like the city going out and removing all of the leaf piles, and they would follow that up with a street cleaner, and then we would have USGS personnel out there with leaf blowers right before a storm and clear off the streets to keep them as clean as possible. And so here's the result of that effort, and we're looking at the same chart we saw earlier, but now we have a new red dashed line that shows the treatment condition, that maximum leaf removal effort. And you can see the results are fairly dramatic. We have essentially a baseline concentration all the way from April through November. We no longer see that large spike in October because the leaves are no longer there. So this gave us confidence that, yes, by removing the organic detritus and leaf litter in the fall, it produced significant reductions in phosphorus concentrations and load. Now we can start moving on and testing other municipal leaf collection practices in confidence and be able to quantify those. The other thing that we took away from that first go-around was a couple of things. If you look at the chart on the right, and we wanted to be able to sort of portion the phosphorus yield by season. Now, we're not talking about winter here. Winter was excluded because we didn't monitor in winter. So we're just talking about spring, summer, and fall. And a couple of things. First of all, when you don't have any leaf collection, clearly you have a much higher overall total phosphorus yield in that urban catchment. And when you do have leaf collection in the fall, as you can see in our test catchment, that overall yield really reduces. So we went from 2.5 kilograms per hectare down to about a little less than 1 kilogram per hectare. But the other thing to take a look at here are those pie charts. And when we start distributing the total phosphorus yield by season, if you don't have leaf collection, the majority of your phosphorus yield comes in the fall. And in 2015, that ended up being about 56% of the annual phosphorus yield came in the fall. And then note the number of storms that 56% came from, where N equals 8. So only 8 storms produced over half of the annual yield. Now you flip that on its head and you say, well, let's get rid of all those leaves in the fall. And then now you can see that pie chart flip-flops between summer and fall. Now summer is the main driver, where you have 3 times as many events, but if you leave those leaves in place, the 3 times as many events, you still have less overall total phosphorus yield in the summer. So again, just adds confidence that removing removing the leaf leader in the fall really does have significant reductions on total phosphorus. Now we can move into our analysis of actual municipal leaf practices, and really it only comes down to a couple of variables. One is, what is the way in which you collect the leaf piles? And in Madison, the way they collect them is what we call the transfer method, and that upper left photograph shows you what that looks like. It's essentially a vehicle that pushes the leaf piles into the street and then into a garbage truck, and they haul them away. That is then followed up by a street cleaner, either that same day or a day or two later, which would either be a mechanical broom, which most cities use, or maybe something a little bit more sophisticated like a regenerative air or a vacuum assist type sweeper. Another leaf collection method that's commonly used in Wisconsin is a vacuum mulching system. There's other ways you could do it, but we needed to kind of find out where we could get the biggest bang for the buck here, and this is the way most cities around Wisconsin collect their leaves and follow up with street cleaning. That third bullet is really, I think, the main driver here. It's how often do you do this? And I'll get into that a little bit later. So we together, after surveying a lot of the cities around the state, asking them, well, how do you collect your leaves? We came up with this matrix of various combinations of leaf collection method and frequency, street cleaning method and frequency, and broke it down into what we would consider either a high overhead tree canopy or a medium overhead tree canopy. I don't have a lot of results on the medium tree canopy, so I'm going to focus the majority of this discussion on the high overhead tree canopy. So this is the take-home slide. This is the bottom line for each of these different types of municipal leaf collection practices. I'm showing you both the percent reduction for each of these different types of practices for total phosphorus and dissolved phosphorus. But I'm going to focus the discussion on dissolved phosphorus only because the majority of total phosphorus is in the dissolved phase. And if you think about it, you have those piles of leaves, a lot of organic detritus on the streets, it rains. A lot of those leaves don't go anywhere, except for maybe the most intense storm events. And so what you have is this tea-like brew of stormwater where the majority of phosphorus is leached out of those leaves in the dissolved phase. We see up to about 80–85% of total phosphorus is in the dissolved phase during the fall. So focusing only on the chart to the right, you can see that for our maximum effort, on the far left column, we have over 80% reduction from that effort alone. So that was at a 95% significance. And by the way, each of these bars are color-coded by their significance. I felt it was important to go down to roughly 80% significance. Not everything has to be at 95 in this case. And then we start stepping down, and those next three bars, highlighted there by the red box, are all roughly about 65% reduction. And if you look at the nomenclature down below, there's sort of a letter number combination, and that first letter represents the leaf collection method, and the first number represents the frequency. And then the second set of letter numbers would be the street cleaning and frequency. And so if we look at V1-R1, that represents a vacuum mulching collection system done once per week with regenerative air street cleaner done once per week. And so really the only thing I want you to take away from this slide is that those three bars at all roughly 65% reduction have different ways to collect leaves, but they have the exact same way the street cleaner operates and at the same frequency. So I think, in my opinion, the take-home message from this slide is that it really doesn't matter how you collect the leaves. What's most important here is how clean is that street before a runoff event. So when and how frequent do you deploy your street cleaners, and how efficient are they at cleaning up those streets? Stepping back a little bit further now, going off to the right of that chart, you can see now we've gone to a T2M2, which means the 2 is once every 2 weeks frequency. And this, by the way, is what the City of Madison does, where they have a transfer method with a mechanical broom sweeper done every 2 weeks. And that's roughly a 45% reduction. And then when you have only a vacuum collection done every 2 weeks with no street cleaning, now you're down to roughly 30%, but also our significance tends to drop. And finally, that furthest to the right shows our only medium canopy result, where again we're operating on a once every 2 week schedule, and there we show no statistical significance at all. So again, more leaves means more organic vegetation in the street, more leaf litter. The more frequently you're out there, the more reduction you're going to get. So as a result of that first effort, the Wisconsin Department of Natural Resources issued a phosphorus reduction credit for leaf management programs that each of the permitted cities in the state could accept as long as they followed certain criteria and guidelines within that document. It was initially set to 40% reduction based on early research efforts. I think they're now in the process of trying to upgrade that to a 60% reduction credit. So where are we going next? Well, we're in our final year, and I think we could obviously continue on that course of evaluating different types of municipal practices. There's bagging, there's other ways that you could do it. We weren't able to cover all combinations and permutations of how cities do it. But for now, we're going to summarize the results we have. A paper will probably be coming out within the next year. But looking long term, the ideal goal here is to take what we've learned, the data we've collected, and incorporate it into some sort of predictive model. Probably something like WinSlam, because there are already street cleaning functions within that model, and a lot of cities within the state of Wisconsin use that to help determine their TMDLs. Another possibility is to start looking at iTree, and there is an iTree species module where you could potentially determine the phosphorus content of leaves by species, different species, as a way to determine which trees should we plant in an area that might help us minimize the amount of phosphorus contributions to stormwater in the fall. We're working with the University of Wisconsin-Madison, some graduate students there who are developing first order decay function leaching rates that will tell you, based on different types of leaf species, how much phosphorus leaches out over a certain amount of time, and we'll continue to work with them to help develop those equations and hopefully incorporate them into some type of model. That's stay tuned for that. That's in the future. Okay, so that was the research project talking about stormwater quality. Now I'm going to shift gears a little bit and talk about a relatively new project that looks more at stormwater quantity and how urban canopy can help minimize the amount of stormwater volume that ends up in storm drains during precipitation events. This is a collaborative effort with US EPA, Forest Service, University of Wisconsin, and the city of Fond du Lac. So as part of the Great Lakes Restoration Initiative, a lot of grant applicants who decide to be planting trees in some shape or form usually need to report how many gallons of stormwater their project plans on reducing. And right now this is kind of done by a very simplistic formula where you're given 59 gallons per tree per year. And working with EPA, there was a lot of question as to, well, how accurate is that number? Can we be more definitive by looking more closely at individual tree species? What does it mean if we roll that up at the neighborhood level or the urban catchment level? So that was sort of the idea behind this particular project, was to start drilling into that number and seeing if we can't improve upon it. Realizing, of course, that measuring these stormwater volume reduction of individual trees is highly variable based on individual species and quite difficult to measure. But nonetheless, we took this on as a good challenge, and our primary goal here again was to incorporate a paired basin study design. And we're looking at tree removal as a proxy for how much stormwater those trees kept out of the storm drain. And so the idea is that, again, we have two different catchments. On the right photograph, you can see we have two catchments here located in Fond du Lac, Wisconsin. Again, this is a medium density residential area. And those green dots and red dots on the graph to the right represent tree canopy. The red dots are green ash trees. And each of these trees, each of those red dots are scheduled to be removed because of the infestation of emerald ash borer. So this is a great way as scientists to come in and be able to do a paired basin study design where we can measure the hydrologic response of these catchments with the trees in place, and then follow up again a year later after those ash trees have been removed and note the difference in the hydrologic response. And then we can start quantifying that and assigning that change to the trees as a cumulative response. So where we're at right now, we have a calibration period done. 2018-2019, we had monitored and characterized the hydrologic response with the trees in place. I would imagine that within the next month or two, those ash trees are going to be removed in the treatment catchment, but the trees in the control catchment will all remain in place, at least for another year. So we don't have a lot of results to talk about, but what I will do is tell you a little bit of how we're approaching our study design. And, realizing that trees do not just intercept precipitation alone. They do a heck of a lot more than that by drinking up the water and the soil moisture, reducing soil moisture, preparing that for the next storm event, allowing more infiltration, perhaps increasing evapotranspiration, et cetera, et cetera. So we wanted to incorporate a fairly comprehensive monitoring effort to look at the entire urban water budget and not just individual trees or not just monitoring the end of pipe flows. So the urban water cycle looks, I'm sure we're all familiar, but it's essentially we're looking at the runoff, the precipitation, ET, infiltration, and storage. And then in parallel to that effort, folks at the U.S. Forest Service and the Davey Institute are working on modeling this, each of these catchments using the iTree hydro module, and then taking the data at a very hyper-local level and incorporating it and perhaps augmenting some of the functions and algorithms that are within that model to make it more efficient. So I'm just going to kind of step through how we're monitoring each of those components of the water budget and then focus in a little bit more on some of the tree canopy results. Our first effort here, and this is really the take-home at the bottom line. At the end of the day, we're going to note differences in surface runoff, the hydrologic changes with trees and without trees. And we're doing that by monitoring the end of pipe flows. We're lucky enough that both of the runoff points in the storm sewers meet at one location, so we can monitor both the test and the control catchment at one point. And so far, based on the last couple of years, we have a really nice relationship between both the test and control catchments in terms of storm volume. Ideally, you want to see a really nice high R-squared value here, and we have that at about 0.95. The tighter those dots are together, the more likely we are to be able to detect a change next year once those trees are removed. And what I anticipate, or what I hope to see, is what this red dash line shows you, is that we're going to, once the trees are removed, we are now going to have a shift in our test catchment where we're going to have more runoff because those trees are not there to intercept some of the precipitation. We'll end up having more runoff than we previously had with the trees in place. So stay tuned for that. I would say probably by this time next year, I'll have that line more definitive. So in addition to that surface monitoring point, we incorporated 6 what we're calling our arboricultural hydrologic measuring parameters. We have 6 of these, 3 of them in the control catchment and 3 of them in the test catchment, where we're looking at what's going on at the tree level. And that includes sap flow sensors. We have a tipping bucket rain gauge that measures through fall. We have a multi-point soil moisture and vertical profile. We have groundwater, a groundwater well for groundwater level observations, and then stem flow measurements as well. And these are located on ash trees and maple trees. So I'm going to talk, in the interest of time here, I'm just going to focus on canopy interception and a couple other parameters. if we take a look at that top left chart, now we're looking at the monthly median interception depth for each of the 6 monitoring points. And you can see they kind of by month jump up and down, but generally bounce between 0.05 and 0.15 to 0.2 inches of canopy interception. And this is generally consistent with what the literature reports for these particular types of species, green ash and Norway maples. And if we summarize those in the chart on the bottom and we kind of roll them up by street level, we have our our test and our control catchments. Again, the interception depths they don't fluctuate a heck of a lot, generally around 1/10 of an inch or so. And then up to the right, you can see that we can accumulate that and sum that over the monitoring period for 2018 and 2019, so that you can see we have anywhere between 5 and almost 8 inches of precipitation that was captured within the tree canopy over that monitoring period. And why do we need that? Well, now we can start playing some games, and I can say, based upon that interception depth, I can then apply it over the area of the tree canopy that resides over impervious surfaces. The idea being that if that tree wasn't there, this is rainfall that would hit an impervious surface and most likely run off. Then we can use that to compute a volume to determine, well, how many gallons of stormwater did we really keep out of the storm drain, just by the interception alone. And you can see for 2018 and 2019, it ranged anywhere from 80,000 up to almost 150,000 gallons. Now, and this is just this one small area. And you might ask, well, why are those 2 years different? Well, one is that the total rainfall was different for each year, but the other is the characteristics of the rainfall were a little bit different, in that in 2018 we saw many more storms of a much smaller precipitation depth. And I think these are the storms that are much more efficient, or trees are much more efficient to capture a larger percentage of the total precipitation depth. Whereas if you get up to, half inch of rainfall, the trees essentially have reached their saturation point and they're no longer effective. Well, the other thing we can do then is take that total volume of precipitation that was intercepted and apply it across the entire tree canopy for the city of Fond du Lac. And this is something the Wisconsin DNR did an analysis using iTree and came up with this possible urban tree canopy area. And the existing tree canopy right now is almost 2,000 acres. If we apply that range of roughly 5 to 8 inches of interception that was measured over those years and over the 2,000 acres, now we get anywhere from roughly 300 to over 400 million gallons of stormwater that was kept out of the storm drains just by interception alone. This is a fairly crude number. It's a back of the envelope calculation, but at least now we can kind of get some sense of how many gallons of stormwater are we talking here, and that's not insignificant. The other thing we realize, of course, is that a single tipping bucket rain gauge underneath the tree canopy probably does not capture the variability of what actually made it through that tree canopy. So we're conducting experiments now with the University of Wisconsin is doing these bucket tests where we create a grid of individual buckets underneath the tree to try to determine what is that variability. And if you look at the heat maps to the right, you can see that the depth of water is not universal. It's not constant. And so what we're going to have to start working on is being able to develop these corrections to what we're measuring in our tipping bucket rain gauge so that we can get a better sense of what the actual through-fall characteristics look like for each storm. The other thing that the University of Wisconsin is working on is this idea of being able to develop a canopy interception model by using accelerometers. And accelerometers are essentially the same things that you and I have on our cell phones that determine when we're walking. Same sort of technology is used in the tree, where you can put an accelerometer up in the tree, and depending on how much water that tree retains will ultimately determine how much sway, how far that sway the tree is. If you think more water, there's more mass, there's more sway. And we can use this sort of information then for each individual storm to isolate and determine where we have an increasing sway period. We know that more water is being retained. And then with a decreasing sway period, we know that the water is most likely evaporating and drying after a storm. And then that can be rolled into a total volume of precipitation that was intercepted by the entire canopy itself. Then this information, when you get enough points, we can start regressing what the interception depth is to what the sway period differences look like. And if you get enough of dots on that graph, you could get a relative confidence in your regression that you can then take an accelerometer in a different tree. You don't have to worry about the actual interception. You can just measure the sway period, and these things are cheap and very easy to install. You can get a lot of different, a great deal of information in a short amount of time. That's sort of a tangent to this project that we're still working on. Sap flow sensors I mentioned. This is the idea behind a sap flow sensor is that you're basically injecting a pulse of heat at the lower probe, and the upper probe then measures the difference in temperature, and that difference is due to how much water is being moved up through the trunk of the tree. And what it allows us to do is determine the magnitude and direction of the water flux and be able to calculate a volume of transpiration for each individual tree. And it looks a little something like this. Don't worry about the blue dots. I draw your attention only to the black lines, where basically what we're looking at here is that transpiration rate for a 12-hour period, or excuse me, a 24-hour period, so every day overlapped on top of each other over the monitoring period. So that's why you see sort of out of a cluster of black lines laid over each other. But they tend to kind of coalesce into a single, average type of transpiration rate in millimeters per hour. And really the only thing to take away from this is that our ash trees look fairly similar to one another. And the maples are larger than the ash. Maples that tend to drink a little bit more water during the day than the ash. And that we can then take this information and get a much more accurate transpiration rate for the trees that we're monitoring, and then broadly apply that to all the others within the catchments. And the other thing to note here is that even though we're going to be applying it to trees that aren't monitored, it's somewhat of a lumping. The thing that we should note in that lower left chart is that not all trees are equal, and this particular maple tree you can see is unlike the other maple tree where there really is no transpiration going on, and that's because this particular tree is diseased. And so it became pretty clear once you look at the transpiration rates. It's not moving much water. So finally, we take all of these elements, and again, the idea is to incorporate them into the urban water budget, and then identify where each of these parameters are contributing and the percentage of total runoff, total volume of water. And we've done this so far for the 2 monitoring years of 2018 and 2019. But again, both of these years, all of the trees are in place. We know what the precipitation volume is. We know what the runoff volume is. We have estimates of what the storage in the canopy is. And then we have measurements of evapotranspiration, both in an open area where the vegetation is exposed to sunshine, but also measurements in shaded areas where temperatures are different, radiation is different, so we can break that out. And then finally, what was infiltrated in depression storage and other types of storage. And really, the thing to take away from this one is that we have essentially the exact same percentage of water that is captured in the tree canopy. For both catchments in 2018, it was 5%, and in 2019, it was 5 and 6%. So generally, that was a smaller number than I was expecting, but interesting that it was almost the exact same number. The other thing to just note here is that evapotranspiration, I think, is going to be a pretty important player in all of this. These are relatively rough numbers, so they're going to be refined over the coming years. And again, next year at this time, we'll have hopefully a new distribution once those trees are removed, and ultimately I'll be able to apply a final volumetric number to what tree canopy does in terms of keeping volume out of storm drains.